In this set of videos, we've already done the multiplying, so we're going to go ahead and divide radicals. And this also comes with a big idea that is very important you understand. If we have the nth root of A divided by the nth root of B, we get to combine those and rewrite that as bring the A and the B underneath the square root symbol. So this is essential that you understand that. So let's go ahead and see how it works. The square root for number example 1, the square root of 6 divided by the square root of 2 is the same as the square root of 6 over 2, and we know that 6 divided by 2 is 3. So the square root of 6 over the square root of 2 is equal to the square root of 3. We can't simplify that anymore, so we leave it alone. For number 2, we have the square root of 3 over the square root of 27. Well, using our big idea, we know we get to combine what's underneath the radical. And anytime you have 3 divided by 27, anytime you have a fraction, you are certainly allowed to simplify that fraction. We know that 3 goes into 3 one time and 3 goes into 27 9 times. Well, now under the radical we have a 1/9, so that's okay to do that. So we have the square root of 1/9. We can look at this as 1/3 because 1/3 times 1/3 is equal to 1/9. But I think it's a little bit easier actually to go to reverse the big idea. And now we have our fraction under the radical. We can rewrite that as the square root of the numerator over the square root of the denominator. I think this is a little bit easier to visualize. For me it is anyway. Because I know that the square root of 1, that's a perfect square, so the square root of 1 is 1, and the square root of 9 is 3. So the original expression, square root of 3 over the square root of 27, simplifies to 1/3. All right, well, let's take a look and see it. We crank up the level of difficulty here a little bit, and let's go ahead and notice here that we have a fifth root, and so since the roots are the same, you can't combine what's underneath the root symbol if the roots aren't the same. So since the roots are the same, we're going to combine the 4 and the 128. So 4 over 128 gets underneath the radical sign, and then we know that 4, since these are both even, if you think about dividing 128 by 4, I first divide it by 2, I get 64, and if I divide that by 2, I get 32. So that means that 4 times 32 is 128. And so what you end up with is the fifth root of 1 over 32. So if we know our fifth roots, if we know our powers of 2, we know that 2 to the fifth is 32. So we have a perfect fifth root right there. And so we're going to rewrite this. Again, we're going to reverse the big idea, and the big idea, reversing it, means that we can rewrite this expression as the fifth root of 1 over the fifth root of 32. And 32 is 2 to the fifth. So we know that the fifth root of 1 is 1, and the fifth root of 32 is 2, because 2 to the fifth is 32. So therefore, the fifth root of 32 is 2. Now, number 4, go ahead and pause the video and try this one on your own. We have the cube root of negative 12 over 3, and negative 12 over 3 is negative 4. We don't want to leave a negative under the cube root, under any root for that matter, so we know that 4 is not a perfect cube. It's too small, but we can pull out a negative 1 from underneath the cube root symbol, because we know that anytime you have a negative under a cube root or an odd root, you're going to have a negative on the outside. So that's because you can always write that as, so here's the reason, you can always write that as cube root of negative 1 times negative 1 times negative 1 times 4, or 2 times 2. So we don't have a group of 3, but we 2's. We do have a group of 3 of negative 1's. So we get to pull a negative 1 out, and negative 1 times anything is just like the opposite of that thing. All right, I'll save the next few examples for the next video.